Today we're going to be talking about how to find the volume of the parallelepiped, also sometimes pronounced the parallelepiped, determined by the vectors. And in this particular problem, we've been given three vectors, A, B, and C. A is 1, 2, 3, B is -1, 1, 2, and C is 2, 1, 4. Now, if you're not familiar with the geometric figure parallelepiped, basically what it is the three-dimensional equivalent of a parallelogram. So in the same way that a square, when you make it 3D, becomes a cube, right? A cube is the 3D version of a square. A parallelepiped is the 3D version of a parallelogram. So if we have a parallelogram like this, and then we want to make it 3D figure, we can draw a 3D parallelepiped like this, and that's a parallelepiped. We want to find the volume of that if these three vectors define this parallelepiped. And the way that we look at these vectors, basically we can think about a three-dimensional coordinate system, which we'll draw using the right-hand rule, where we have x, y, and z coordinate axes. And our parallelepiped, in the same way that when we want to find the volume of a cube, we're looking for length times width times height. When we find the volume of a parallelepiped, we're looking for length times width times height. So we're going to be trying to find the area of the base and then multiplying that by the height to get volume. If we have three vectors, and I'm not going to try to accurately draw A, B, and C here, I just want to show you a picture, a general picture of a parallelepiped so you can get an idea. If we have three vectors, and we'll call these vectors here, maybe this is B right here, and we have a vector which we'll call C, so we're going to call this one C, we're going to call this one B, and then we have some third vector like this, A, we'll call this one A. So if I have three vectors like this, all I have to do is fill in the other three sides to see how these three vectors define a parallelepiped figure. So I can draw parallel lines like this, and now all of a sudden I have this three-dimensional figure. If I want to, I can make it transparent and pretend here that we can see through it like this. But I have this three-dimensional figure and I want to find the volume. Well, what I'm going to do, like I said, is I'm going to find the area of the base, which is basically the plane CB. So I have this plane here, CB, and that's going to be defined by the bottom of my parallelepiped figure here. So I'm going to find the area of that base, then I'm going to multiply it by height. Well, how do I find the area of this plane? What I'm going to do is take the cross product of B and C. Once I have the cross product of B and C, that's going to give me the area of the plane. Then I'm going to take the dot product of A and my result, and that's going to give me volume. Essentially, I'm doing length times width, and then when I get my result, I'm multiplying that by height. So I'm going to do the dot product of A and the cross product of B and C. Like this. This value is called the scalar triple product. Whenever I take the dot product of one vector with the cross product of the other two, this whole value can be called the scalar triple product, and that's going to give me the volume of this figure. The best way to find the scalar triple product is to first find the cross product of B and C. So we'll take the cross product of B and C. What we need to do is set up our matrix, and I'll go through this kind of quickly because we've already talked about cross products. So we have I, J, and K in our first row, the vector B in our second row, -1, 1, and 2, and then the vector C in our third row, 2, 1, and 4. When we take the discriminant of this matrix and we break it out into its discriminant pieces, what we've got here is 1, 1, 2, 4, times I. Remember, we take everything that's not in I's row or in I's column. That's this square right here of 1, 1, 2, 4. We multiply that by I. Then we subtract the same thing for J. What's not in J's column here is -1, 2, and 2, 4. Multiply that times J. Then we add the same thing for K. So what's not in K's column is -1, 2, 1, 1, and we multiply that by K. Now when we simplify, we take the upper left times the lower right, so 1 times 4, which is 4, and then subtract the product of the lower left and upper right, 1 times 2, which is 2. So 4 minus 2 times I, minus negative 1 times 4 is negative 4, minus 2 times 2, which is 4, times j, plus negative 1 times 1 is negative 1, minus 2 times 1, which is 2, and multiply that there by k. Now if we write our result over here, 4 minus 2 is 2, so we end up with 2i. Negative 4 minus 4 is negative 8. We have minus a negative 8, so that's plus 8j. And then negative 1 minus 2 is negative 3, so minus 3k. We can also call this, remember this is the cross product of b and c, we can also call this 2, 8, negative 3 when we just take the coefficients on I, j, and k. Now, in order to find the dot product of A and this cross product of B and C, we're just going to do A, 1, 2, and 3 times 2, 8, and negative 3. Remember that the dot product, all we have to do to get A times, we'll call this B times C like this, our dot product, we're going to multiply our inner components together and then get the sum of all of those products. So our x components are 1 and 2, so we multiply those together, 1 and 2. Then we add to that the product of our y components, which are 2 and 8. And then add to that the product of our z components, which are 3 and negative 3. And then we just simplify. 2 times 1 is 2, plus 2 times 8, which is 16. 3 times negative 3 is a negative 9, so we get minus 9. And when we simplify that, we just get 2 plus 16, which is 18, minus 9 is 9. What this tells us is that the volume of our parallelepiped is equal to 9 when that parallelepiped is defined by these vectors a, b, and c.